Thanks, with you. Yes or no?
Yes, doctor.
Okay, yeah. So as I mentioned earlier, this one, yeah, I have it. If I mention here, for example, yeah, I got problem with my writing pad. Yeah, hold on, huh? As I mentioned earlier just now, if you're talking about, for example, if you're talking about, okay, you're talking about this one, for example, let's say this one. Yep. No, no, Makam. Okay, this one, yeah, this one. Of course, this one the amplitude. This one, yeah, will be the omega f. Oh, sorry, omega. So it be oscillating quite a while, oscillating and oscillating and oscillating. So you found that in the amplitude is about the same, constant. This one, when you found that no damping, no damping. Yeah. So in other words, yeah, if you again with the same phenomena, you are, so this one can be also be in the form of, for example, you have a mass spring. This is X. Okay, this is M, and you push a bit here. You push down a bit, X, for example, then you let it go. It will be displaced, then it will be oscillating with different velocity. It will give you acceleration. So these three, X, X dot, X double, we call the vibration amplitude. This is vibration amplitudes. Yeah, vibration amplitude. So you found that the vibration amplitude will be in the form of displacement, velocity, and also an acceleration, isn't it? So if you have another system, for example, here, where today's our today topics, you have mass, you have the spring here, but then you have another device, damper, so-called a dashpot, and in other in mathematical denotion denotes here as a C. And again, you still be giving x. There's no x. This one f equal to 0. This one also same thing, f equal to 0. So it will still x, x dot, x double dot. But due to this presence of this damping, this one, yeah, this is a damping, we call damping this one. Due to the presence of damping this one is a damper. And the damper is a dashpot. This one, C is equal to 0, so we learned last meeting. So due to this presence of damper here, so your vibration amplitude will become a bit different from what you have earlier. Will be oscillating, yes, because you give the displacement just now and you release it. This one is omega, of course, omega n, yeah, omega n, because there is no external, external force, yeah. So it be oscillating quite a while. Then it will keep what? Reduce this one. This the amplitude. This is the amplitude. The amplitude becomes smaller and smaller, then vanish. This one, the amplitude is vanish. Or sometimes we call decaying. Decay or die. Vanish, decaying, or die. So as this one will die, so it simply means that it will stop. Of course, it will stop. Correct. Finally, it will stop. By looking this one, so the arrangement, or perhaps the, what do you call it, yeah, the peaks, if you measure from peak to peak, you measure from peak to peak, every amplitude of vibration, you measure this one, that you found this one, what we call as exponential line, exponential line. So here, the x is equal to x naught that we learned earlier, sine omega nt, no longer valid. No longer valid. Because it is not in the form of simple harmonic motion at the reduction of the, because why? Yeah, because due to the presence of the present CE, yeah, the present yes, presence of reduction of amplitudes, meaning that amplitude becomes smaller and smaller. Amplitude become smaller and smaller. Then, decay. Decay. Okay, so that is the term why we study damper. Okay, so the equation that we use, this one in our last topic, will not be valid anymore. So you will have the another amplitudes. Sorry, another in term of equation. You know well that this equation now is, we are talking about exponential. I think everyone agree with me. Exponential simply mean give you the x equal to exponential this one, isn't it? In term of this equation now. Remember the thing that you study couple of years in the what in this in your mathematics typically. Okay, so I will stop sharing this one. I'm going to go back to the what the first slide just now. I'm going to share with you here. Then of course vibration, as I mentioned a couple of times about vibration, is basically when you disturb a system, then it will vibrate. If you're not disturbing the system, for example, the system will be keep it keep stay still. For example, there will be no vibration. Yeah? Yeah. First degree and second degree I already mentioned in our first lecture. First degree mean that you are basically categorizing the system is only oscillating in one plane or in one character or in one behavior, which is x. This is x only, or perhaps you can call it an x1. Okay, this one, the second one, don't bother to copy. You have this one, this note. Very sorry. I passed your note. It's quite late. I basically forgot about your new notes. Okay, this one is thing to discuss in our class. First, what is damping? I did mention a bit about damping earlier. What is the damping ratio? Of course, when you have damping, you will have the damping ratio. Same thing like friction. We have friction, then we have coefficient of friction. Of course, in the coefficient of friction, we have coefficient of friction static and also dynamic. Here, there is no damping static, no damping dynamic. Only damping ratio, or sometimes called coefficient of damping. Same thing. Beside that, you have a damping constant. Very much alike when you have a spring constant. This one damping constant, meaning that it will be a units, but unit will be constant, for the whole analysis or the exercise, for example. Then we're going to look for type of damping. You have three type of damping: hysteresis, Coulomb, and also friction. That's one we're going to talk about the one, in detail. And the three cases that we're going to look for, very much interested. This one, very much important here. This one is over dam, is under dam, and also critical dam. Why we are going to look this one is basically the important thing to what they call it, to recognize whether you are dealing with under dam, over dam, and critical damping. The three type condition, this one will be depending on the damping ratio. The damping ratio is called as zeta, Z-E-T-A. It's a zeta, Z-E-T-A is a zeta for damping ratio. The damping constant, as I mentioned earlier, is C, the units of Newton second per meter. And the other part, as you know, this one logarithmic decrement, the logarithmic is a mathematics term. Decrement is basically reduction. Decremental is basically reduction. So if you are talking about logarithmic decrement, it's basically logarithmic reduction. So it simply means that the amplitude becomes smaller and smaller and smaller, but in terms of logarithmic, or logarithms. This is logarithm base 10. Okay, we have this one, another equation to define what will be the exponential graph look like. Together with that, we are going to talk about something like here, what method of solution. Again, we are going to look for Newton's law, energy, and equivalent. We're going to prove the three methods will give you the same results at the end of the day. And then, of course, we're going to look for the work example. Couple of examples provided in your books. I'm going to explain, not in detail, the example provided in your book. But of course, in other material that is not provided, inshallah, we're going to do this one in detail. Typically in the past test and also exams. Okay, this is damping. We start with damping because we are dealing with now free damp vibration. So what is the damping? Damping in Wikipedia I mentioned about this one. You can read on your own. Damping is an influence within or upon an oscillatory system that has the effect of reduction or reducing, restricting, or preventing its oscillation. This one, yeah. And you know well that when the amplitude becomes smaller and smaller, as mentioned or perhaps illustrated by the graph beside the spring mass system here, you found that what energy also been dissipated, isn't it? Energy also been dissipated, meaning the energy becomes smaller and smaller and smaller, and that is why the energy conservation will not be present in this kind of topics. So look at here, a simple analogy here. You have a mass and spring here system, then you put in water, and of course in water perhaps it could be very good in observe. It's not in water. Yeah, you put in oil, for example. You know that oil have a very thick viscosity compared to water, isn't it? So the viscosity of the liquid will be depending on how easy the system or the mass here will be oscillating. For example, this one, if you put water, it's very much good oscillating, but you put oil here, very difficult to oscillate. So you found that oil and water have a very much different in amplitude of vibration. Okay. In my class, yeah, I do bring this one in my class a couple of years back. I showed the student how is the basically in terms of damping phenomena, perhaps, yeah. And of course, in the engineering perspective, there is no water, there is no fuel, oil, but you will have what we call as absorber. Absorber is basically to absorb energy. It doesn't matter we are talking shock absorber or continuous absorber. And basically, it is the device in engineering world to absorb energy. Okay, this one is another we call it analogy. The first one, if you look at the top left, this one, yeah, can you see the graph, the animation class? Don't let me talk to myself here. Hello. Yes, thank you, Leah. Look at here. The first top left on left, you found that there is no damping what you call device. So the oscillatory, for example, yeah, will give you the same amplitudes. Look at the dot here, the red dot representing the movement of the block, red block. So in horizontal, and we are find that there's no phase involved here. Okay, we keep oscillating and oscillating, then it will give you the amplitude. If you look at the amplitude here, from 8 to 4 is basically 4. For positive 2 and positive 2 and negative 2 will give you 4 units. We do not know the unit now. We can put 4 units. If you're talking about centimeter, could be 4 centimeter. For the oscillatory measured is from the highest level or the highest peak here to the lowest valley. Okay, to the ultimate height to the ultimate lows. Okay, look at the other one, right, top, bottom right. Look at here. You found that if you look at the graph itself, you find that the amplitude becomes smaller and smaller, and it will diminish. Correct. And look at the analogy here. You have a mass of M, you have spring, of course. Then you have a plunger here. Plunger, plunger, meaning that the dashboard. This is a plunger, and this plunger will be acting as a damper. So it will be absorb energy, isn't it? From natural oscillatory, then it will be keeping the amplitude become smaller and smaller. Then you know it will creating this one. If you draw the line between all the peaks, it will give you what you call it just now. An exponential. Then it will create you exponential graph between all the amplitudes, isn't it? Okay, move on to next one. This is the how do we from the actual thing here we put it in the mathematicals. This one is in mathematicals. Damping vibration in mathematical. Look at this one. Look at the graph. As engineer, when you put figure, it's much easy to explain rather than put all the numbers or sentences. Look at here. You have M, then you have K and C here. Then you give X. You pull a bit or you push a bit, then you let it go. Isn't it? As you release the system, it will be oscillatory a bit, couple of cycle. Then while oscillatory, we pause a bit because we are going to look for free body diagram. Then you have M here, of course. If I can draw here this one, this one is this one, yeah. This is basically I'm sorry because it's very difficult for me to use this one annotate, yeah. I tried to do annotate couple of times. I did try this one but failed because I don't know whether my writing pad is not good, or perhaps this software is not so friendly, yeah. So this one, look at here, very difficult for me to write here, isn't it? Here, look at here, very difficult. This one is basically mx double dot, isn't it? Mx double dot. So this is the motion. The motion, very difficult to write. Okay, never mind. This is the motion. And you know that this one is the one resistant to motion is always opposed the mx. Mx pointing that way, the resistance will be pointing the other way. So you have kx, cx. That if you make the equation, for example, what do you have? You will have negative kx, negative cx is equal to mx double dot, right? Okay, we are going to do this one so many times later on. So this one just to share with you that this kx is basically, sorry, this cx is basically also a part of kx as what we did earlier, as it is again the motion of mx double dot. So now, then finally, your result, your equation be this one negative is just telling you that, or telling us that it will be pointing again the motion. Okay, this one again, this is the definition of free damped vibration in your book. You can turn to page 270. So it will give you, or precisely mentioning about the free damped vibration system that you're going to look for. So in free damped vibration, the amplitude of the resulting vibration gradually diminish. Diminish means that it will vanish, it will die, or perhaps dissipated. And this is due to the result certain amount of energy is always dissipated. Dissipated means been absorbed by the dashpot just now, to overcome the frictional resistance. In small, if damping is small, very little effect. So if damping is small, for example, so your amplitude become very small, then your natural frequency also, very small in difference. So sometimes we do need the small damping, sometimes we do need the small damping, depending on what kind of problem you are dealing with. This one, another animation telling you that, for example, if you drive here, this is a vehicle, look at here, the vehicle, your figure on left hand side, vehicle. Then if it hum, this is hum. So as it said hit hum, this one, you found that the amplitude of vehicle will be different from the initial and after, isn't it? So it will jump, jump here, isn't it? So it can also be presented by the graph. Okay, can also be represented by the graph. So the amplitude after this one, the damping will be the same. After damping will be the same. So because there is no one, because there is no hurdle anymore, isn't it? So the level or the speed is levels. This one another example before damping. Look at here, very damping. You have very high amplitudes. When come to damping, you put something on the system, so it absorbs energy. You find the amplitude becomes smaller here. So this is a good damping system when you have to avoid from the amplitude of vibration, which very annoying for people. Then if you are doing something dealing with rotating machinery. Okay, we move to the next one. Hopefully this one will will help you to understand what is damping, why we need damping so much in our life. Another damping material is not always for this one, is physical term, in the amplitude become in physical, isn't it? But if you have put the ear plug, isn't it, you use ear plug here to avoid noise, for example, it's also damping, because why? The sound that received by your eardrum is very small compared to the sound that come out from the source. So it's also damping, but this is a noise damping. We call it noise reduction. We are going to learn this one if you join me, inshallah, in the later year of your study. So this one is the type of damping. Remember, I did mention about you need to know about the three type of damping. One will be Coulomb damping. Sometimes we call it resistant or friction. Hysteresis damping, also due to the resistance, but due to the material properties. What that is mean that you don't have to put any extra or auxiliary device to the system. For example, a very good example is a I-beam. You know, I-beam generated or perhaps used to build the bridges or road here. So the I-beam, yeah, if you go through the civil engineering procedure, constructing all these concretes, yeah, the component or the what do you call it, the composition of the concrete, yeah, typically coming from what? Coming from the sand, the gravel, what else? The cement and the water and some other component, yeah, is basically come with composition, certain percentage. So if you have if you give the same percentage, recommended by book, for example, handbook, so you will have the material damping itself. But here, yeah, because we are basically doing the concrete with not following procedure. You just add up water, add up sand, and add up gravel. So you don't basically know how much will be the damping material on the damping characteristic on the material. So that is why if you do in civil engineering, you go back you and look the civil engineering handbook. You know that the I-beam will have the how much damping purpose. This is the important. Typically in the country like Japan, country that very open to the earthquake, for example. We are very lucky, very fortunate. We are staying in Malaysia. We are very, you know, we do experience the earthquake very minor one. Okay, the other one will be the viscous damping. Of course, when you're talking viscous damping, you have something, a device to add on to the system, and it called absorber. And we're going to focus on the third one, this one. The first two, this one and one and two, will not be part of our exercise. The third one will be very much easy compared to the first two. Okay, from now onward, I'm going to discuss about viscous damping. If you want to know about this Coulomb damping or Nernst damping, you need to join the other course 4213. I'm not promoting my course here. I'm basically telling you, if you want to know this one better, you need to go further in our course. Yeah. So the damping element, this one also the same thing. This one only mentioning about what type of damping. This one is describing a bit about the damping. If you're talking about viscous damping here, the first force here, damping force is proportional to the velocity of the vibrating body. This one is proportional to the velocity. Remember this one, damping force is proportional to the velocity. What is the force? Spring force. Could anyone describe what do you know about the spring force? It also proportional to what? The spring force. Anyone can answer that one? If damping force is proportional to the velocity, what about the spring force? Hello? Extension, yeah, but we call what? Damping force is the velocity, so the spring force will be proportional to the what? Anyone? Extension is correct. In other words, you study in dynamic or in static perhaps. So what is it called? Extension is when you have the initial and the displacement. Yeah, correct. Go. It's very correct. Damping force is proportional to the displacement. Extension meaning that you have the displaced position and you also have the what? You also have the initial length. So you have the display. You have the extension. Oh, it's also correct. Yeah, but the displacement is very true. Okay, the next one be what is the viscous damping. We go further about viscous damping. You have this one type of damping. The damping or perhaps the absorber here, we call this a common, we call it the shock absorber here, come to the range that a human size and also a very small one. This is the human size shock absorber. You can read on your own this one. Yeah, the dashboard is a mechanical device, damper, so on and so forth. Don't worry about this definition. It will not be part of your explanation in your exam. But perhaps this one, yes. Viscous damping. Damping force is a fraction of the velocity. What about spring port? That one is a part of the engineering practice of defining, term, for example. But this one, like, what is damper? The meaning of damper? The what call it? The component of damper? No, it will not part of our exercise. Okay, one big thing here is what, the slowing the motion and also absorbing energy. This is a big message here. Slowing the motion will be slowing the motion, but as you slowing motion, we do not know how much the motion will be being slow. But what you do know there is the energy being absorbed. Of course, when energy being absorbed, you found that the amplitude becomes smaller and smaller. This is the, as I mentioned earlier, the size of dashpot come from the range of very small size here and to the human size here or man size here. Okay, and in the term of notation is C, and our concern now is to see, we already study K. Now it's time to study C. C is a damping properties or damping constant. This is how it works. You can look book from the very small book you buy in any bookshop. A small book called How It Works. It's very informative about this one. So this one is about the no viscous damping. This one has viscous damping. If you observe buses, for example, the public transport, you put it there, what, air suspension, isn't it? You have the other one is what? Fluid suspension, isn't it? So you found that when you use the air suspension, it's easy to control rather than fluids. The air suspension is just to control the valve in such a way to put how much air in the volumes. So if you an engineer, you know that the car, that the bus can carry 40 passenger, for example, or 30 passenger, for example. But somehow rather than only 1 or 2 passenger now in the a bus, for example. So you can adjust the level of the air in the chamber. So because if you don't adjust, it become very stiff, and person in car in the car in the bus will be feeling not very comfortable. When you adjust it, it become less stiffer, then it will be more comfortable. When you have so many people, then you have to put it more stiffer to absorb all the energy. But when you put on the very typical absorber, like the K absorber, for example, you cannot control what will be the happen on the chamber to absorb energy. Okay, then we saw the air suspension typical for buses is very common and very famous today. The other one is how it's worked. This is the plunger, as I mentioned earlier. This one, the fluid here. So it depending on this one, the hole, how many hole here provided in the plunger. So if you have so many hole and the hole is so big, so you found that more fluid can come through. So you found that it's easy to move. So you can adjust the diameter or perhaps the radius of the holes here to avoid much oil to come through. As you adjust the diameter here, you can also adjusting the damper or the damping properties. This one already mentioned just now. This one F equals CX. This one also, another one is damping variation. Now only we're going to look for the damping variation. Just not only about the damping oscillatory. Occur when the amplitude occurs when the amplitude of a free vibration diminishes gradually over time. Look at here. Gradually diminish gradually over time, meaning that one respect to time. And time with cycle will give you hertz due to resistance offered by the surrounding medium. When you have resistance, it will try to absorb the resistance. Example A here. This one is if you remember the thing that as I mentioned here, the hysteresis damping. Go back here. This one, hysteresis damping is due to material property, isn't it? So we go back here. Then you understand that what is the hysteresis. Look at here. This is no dashpot at all. You found that if you three mass here, the black, the green, and so the blue, and you display the thing with the same displacement, it will be creating oscillatory, and the amplitude is exactly the same as 2 and -2, isn't it? And you have the same system here. You take one here, the black one, put it with blue one, and the blue here has a what you call it, hysteresis damping, material dampings. This one, the spring is, manufactured with the damping properties. So you found that the dark one will be oscillating as the initial part, but the blue one will be oscillating quite a while, then it will stop. So this is what I call hysteresis. So I'm basically want to expose to you system with and without damping. Then you know that we are basically looking at the blue line here rather than the black line. Okay. This is the equation now. Now the equation, come to the equation. So this one is what we have learned earlier, omega n equal to k by m. Now, because you have C now, we are going to another one, omega d. It's a damn natural frequency. If I can share with you another, stop sharing here, I'm going to share with you just now, yeah, these notes here. Okay, what you been learned earlier was, it doesn't matter whether it is supported or suspended, yeah. For example, here you have this one. Okay, this is spring mass. Then you have the free body diagram. Remember, you displace the mass, of course, with x dot, x double dot. What you have is this one is kx. This one is mg. Remember, then you have this one is mx double dot. Sin, remember the static, mg equal to k delta. This one is basically x plus delta. You remember in our work earlier, you found that this ng will not be in the equation. Finally, you can basically ignore the mg because this is due to statics. You can do this one, then you have that, okay, summation of f equal to mx double dot. So pointing downward positive, excuse me, you have this negative kx equal to mx double dot. Correct? Then you can rearrange the equation becoming mx double dot plus kx equal to 0. This one what we call as equation of motion. Or you can also rearrange the equation become x double dot plus k by m. X equal to 0. We call this one, you can call this one equation of motion also. But some book call this one differential equation of motion of the mass and spring system. Okay, now you have another system, same system, but you provide the presence of damper. Of course, we are talking about, when I do talk about damper, is basically the, what do you call it, the dashboard, yeah. Your spring here, you have a damper. Same thing, you displace x dot and become x double dot. So if you put in terms of free body diagram, is this is a free body diagram, you have a mass, you display this one with x dot and x double dot. So you will creating the force, isn't it, from the spring, and also the force coming from x dot here, damper, and equal to mx double dot. So if you applying the same equation as before and saying that pointing downward we consider as positive, you are basically talking about negative kx here minus by cx dot here is equal to mx double dot. And we arrange the equation, it becoming as such, isn't it? And it is not very difficult. So you have a new term here, this one. Correct? And again, yeah, you can also rearrange this equation to become x double dot here is equal plus this one c by m x dot plus k by m x equal to 0. Now is the new equation to us, saying that is the equation of motion of the system that we are dealing with. Or perhaps we can also the differential equation of motion from the spring MS system with damping. So when you have the earlier part, if I can can draw here. The earlier part, what we concern here, remember, we concern about omega n, isn't it? Finally, you're getting mm. You also concerned about t, remember, and we call it now tn. What is the equation of tn? If you remember, what is the equation of periodics or time oscillatory of the natural frequency? Anyone? Anyone? If you don't want to answer, I will keep this one with question mark. You have to look on your own. Could anyone tell me what you have here for tn? No? 1 upon f is correct. 1 upon f is correct. Is correct. Or perhaps in other words, when you are talking about the omega, it's not f, for example. So what would be the equation? What would be the equation? Anyone? Because you're going to use this one so many times, yeah? So I would like you to know this one, because otherwise, it's a problem to you. Anyone? Anyone? Anyone would like to take the challenge? Tan, perhaps, or Ko, Lee? Who else? Walid? Anyone? Okay, we'll keep this one.
2 pi.
Yes. Sorry?
2 pi times square root mo, okay?
That one is the F, correct. But now it's one T only. You have what? Remember? What is the unit for T is second, isn't it? So you must have what? 1 upon F, correct. This one is correct. It's absolute correct because you have omega n is equal to K by M is equal to 1 by 2 pi. This one is omega n, isn't it? This one is radian per second. This one in hertz. I totally agree with you. But I want this one in terms of omega. I want this one in terms of omega. So I want this one in terms of omega. So it becoming what? Pi, yes, correct. Yeah, 2 pi by omega. If you forget about the unit, formula, use the unit as your aims. Yeah, this one in second, isn't it? Is equal to, this one is radian divided by radian per second. So we'll give you second, isn't it? Okay, let us now move to the next one here. So in here, you are going to talk about what? When you have as such here, this one. So it simply means that we'll maintain as omega n as initial. And beside that, there is no Tn now, no more Tn, no more Tn. But it will convert it to become Td. There's no more Tn, but you become Td. So before you have to look for Td, what is Td? Is a damped periodics or damped oscillatory times. Yeah. Before you need to know Td, is you need to know another term is omega d. Omega d is given is omega n, 1 minus zeta squared. Do not memorize this one. We are going to lose this one in detail later on. I just explained this one earlier. So what are the parameters you need to understand before you go further? So then only you have Td. Td will simply give you 2 pi by omega d. This one we call damped natural frequency. Damped natural frequency. Where you found that the omega d is always very small compared to omega. So, and the omega d depending on, sorry, it's not depending on zeta. This is zeta called zeta, Z-E-T-A. And the zeta here is called what? Damping. Damping what just now? Damping what? Damping ratio, or sometimes we call damping coefficient. Damping coefficient. No units. Unitless, yeah? Yeah, no unit. And C here is a damping constant. This is C is damping constant. Of course, sometimes we call damping what? Damping what? Damping value, yes. Damping value. Sometimes we call damping value. Different book will give you different names, but the unit is Newton second per meter. Okay, so that is one you need to know now. We need to know what is the omega d. We also need to know what is zeta, yeah. And when you have this one, you have another so many terms later on. Okay, so let us now move to the theory first before we move to this system. So I'm going to what do you call it? I'm going to this one, stop sharing this one. I'm going to share the earlier part of my note just now. This one. Okay. Okay, yeah, you have T, you have T. So T, this one is presenting Tn. It also can put as Tn. Okay, move on. The next one. This one is one will be you. If you look at it on right on top here, is a shock absorber. What does a shock absorber? Shock absorber is simply that it will be what it will absorb energy when be disturbed. Otherwise, it will be in stationary. And this one what call it shock absorber. Some of the absorber is always in motion. This one shock absorber. There is in your vehicle, yeah, your motorcycle, your car, your lorries, call it a shock absorber. It is not absorber but shock absorber. It will absorb the shock. Here, this one as I mentioned just now. This one is more interesting part. Okay. Look at here, class. This is very important. Yeah. Okay, I'm going to. You have this one. I'm going to share with you just now why this one is suddenly here, assuming the simple harmonic. But the simple harmonic will be in term of what? Will be in term of what do you call it? Exponential. Okay, look at yeah. So now, so as in damping situation, you have the exponential graph. Exponential graph. So what is the exponential graph? The exponential graph is basically saying to us that you have this one, then you have a graph very much like, I'm not good in drawing class, I'm sorry about that. Then it will diminish, and this one will call exponential graph. You have another one, all right? So this one is what measured from peak to another peak, peak to another peak until this one is diminished or become 0. So exponential means that the x is equal to est. Because you have 2 here, you can put here now. This one also same thing. You have exponential x equal to est, isn't it? But we have 2 equations. One will be positive. Of course, this one will become negative. This one is very what call it? Very logic, isn't it? Negative telling that it will be exponentially, but below the origins. So you pick up one here. You put it here. X now is equal to st. This displacement, you have another one. X dot is equal to, is what you have here. X dot be se. St. You have another one. X double dot here. Of course, the x double dot will be with respect to time. You have equal to this one. You have x double to square. This one you have est. Correct? And your equation just now, if you remember the equation that we generated earlier was mx double dot plus cx dot plus kx equal to 0. And we can simplify this one. Yeah? For example, if you want to simplify this one, you know that your x double dot plus c by m x dot plus k by m x equal to 0. Then you try to take this one and put in the equation. As you put in the equation, you'll be creating another equation, which is very interesting here. We're creating another equation which tells you that, okay, this one x dot, put it here. You have s to EST. Then you have plus this one C by M. You have X dot, put it here, S E S T, plus you have X here, E S T. Isn't it? I missed one. Sorry, I missed one. Yeah. I missed one term, K by M term. So you know that the EST is basically what? The common factor. Then you factorize. You have S squared plus C by M. This one S plus K by M. Then you have EST. This one of course equal to 0. Equal to 0. This one of course equal to 0. Isn't it? So your solution will become what? Your solution will become EST, will not become to 0. The exponential cannot be a 0. If the equation is 0, if the exponential becomes 0, so what happened? So if yeah, for example, if the EST becoming 0, so your graph will acting like, meaning to C equal to 0. It cannot be because you have C there. Correct? So it must equal to, not equal to 0. So the other solution that we creating is the X double dot. The X squared equal to this one C by M. This one X plus K by M equal to 0. So this is our concern now. This one, if you check this one, it very much look like what? Quadratic equation, isn't it? So what do you have in the quadratic equation? You have X, or perhaps I start with the equation first, yeah? In quadratic equation, you have X plus BX plus C equal to 0, isn't it? This very much look like the quadratic equation. Then you have the root, remember? Root is equal to X. What is the root now? X minus B plus minus, this one be B squared AC divided by, you have plus minus here, so you'll be getting here X plus anything. Same thing happened to this one. You put this one, let B, this one is A X squared plus B plus C. Then you put all the numbers, all the value here, all the term here. And finally you'll be getting what? You be getting here, put it S1, 2. This one is basically the root. The root from quadratic equation. Okay? So I just want to share with you. Don't worry about this one. This was your what they call it. Yeah, your differentiating of the equation was not part of your works. Remember that you are going to use the equation. I'm telling you this one because when you come to 2-degree freedom, you need to know all about this one. 2-degree freedom, it will be inshallah in coming weeks. So this one, the 1st-degree freedom, you don't bother to know much about the quadratic equation, for example. When you come to this one, you need to use quadratic equation so many times in your solution. Okay, so our aims now, basically, when you come to day 1, if I can go back to the equation, and I am going to back the equation. Feel sleepy? So the weather will, treat you. Okay, now, and finally, so that here I can write something from this equation. From this equation, you put everything, you will have this one. And from this one, you simplify. Okay, then you will have the results. And of course, yeah, this equation is called as what? This one is called as differential equation of motion, but for this system, Look at the next one. This one I already done. This one I haven't done yet. I want to share with you up to here. This one very important. Okay, now, how are we going to create this equation now? The creating of the equation, or the creation of the equation, by what? By assuming. We're going to introduce another term of equation. So now, let assume C is equal to 2m omega n zeta. C is the damping value or damping constant. And let also assume that the omega n equal to k by m. If your equation just now is what you have the equation just now, you go back to the equation just now. We have this one, before that is x double dot, x double, so on and so forth. You found that you can also turn the equation to become some other form of equation. For example, this one, from this one, look at here. This one, and this one very much alike, isn't it? Correct, not very much alike. You can use this one, or you can use this one in your solution. Then you will have this one. So now let's take that you have mx double dot just now plus cx dot equal to kx equal to 0. Then you put the x double dot plus c by m x dot plus k by m x equal to 0. Then you try to induce this one in the equation. So it seems that your x dot will remain as x dot. This one plus the cm here, look at here. C here, m here, so you bring c by m. It will give you 2 omega n zeta. Am I correct or not? 2 omega n zeta. So you bring it here. 2 omega n zeta x dot plus, look at here, k by m is omega, this one omega square, omega n square x. So this one equal to 0. You have another equation. Or perhaps you don't want to put that one, you can also put in terms of what they call it just now, exponential. You will have x square. Look at the equation, this one, x squared, c plus m equal to, this one c plus m is 2m omega n s plus this one omega n square s equal to 0. This one is similar. This one in term of, this one in term of exponential. This one linear displacement. But remember your x just now, you have to remember this one. Sorry, it's not your s. Your e just now, you have to understand that your e just now, your x, your x is now your e, x. You have to remember this one. Then we'll give you the results. Okay? We go back to here. Any question? What is our aim now, basically? So what is our aims now? What is our aim now? Is to generate the general equation for damping condition. This is our aims now. To generate the general equation for damping condition. So we go back to here. So finally, when you use this one, plus all the x equal to est just now, you'll be getting that results. This one. And this is the equation that I'm dealing with just now. What does I say just now? Is the damping, is to generate the general equation or damping condition. So this is the general equation for damping condition, the solution of that equation. Equation. Do you need to memorize this one? No, you don't have to memorize this one. You don't have to memorize this one. This is very easy to understand. Look at the equation. If you can read the equation, if you can check the equation, let me how do I'm going to look this one? This one, look at here. You have x equal to e s t, isn't it just now, right? Your x dot will be equal to s e s t, right? Your x double dot will be s power of 2 e s s t. So this one, if you can put in here, so you'll be getting its results. This here is the root. Remember the root just now? The root is coming from, if I can share you the roots, yeah, just now. Here, this one, the roots. Where are you, the roots? Yeah. You will have the roots here coming from that one, the roots, eh? So don't worry about that one. What you need to know is you need to know this equation. Okay, now I'm going to share with you what is the difference from what you have in the notes and also the equation coming from another books. Look at there. This is very important because when you read book, you sometimes you see you have a different equation. For example, yeah, sometimes books always put you this one. There is no here. They give you sine omega dt. Oh, you put in negative here. So you have so many information about that one. So let us now figure out one thing. For example, yeah. For example, let's say that there is no here. There is no theta here. Your equation up to here. So now, could anyone tell me based on this one, how does the graph look like? If this is very important because you have to read this one whether it's plus or minus or without the sign. This one is what called sign. Could anyone tell me? Anyone? Hello? If you don't want to share with me or you don't want to answer this one, so I will just yes, look at the graph. Thank you. Look at the graph. This one has sign, put it this side. So if this one is there is no sign, so the graph will be start here. Okay. What if you have this one negative? You have omega d, the negative sign. Different book will give you different perspective, of course. So what even when you have negative? What even when you're negative plus? Hello? Anyone? This one is positive, correct? What when you have negative? Minus sign. So what about it? Anyone? No one? Okay, negative you check on your own. This one check on your own because you don't want to respond. More right side it's not more right side because zero start here, starting here. Negative. Okay, because this one will be negative. Okay. Okay, that is you have to because many books give you different equation. Then you start thinking, oh, it could be different, or our equation here is not correct. It's basically correct. So the ideal one will be this one, no side. This one the ideal. Very much difficult to get this one without plus sign. You will get this one. It's exactly here, very difficult. So you have negative or plus. That one in practical. But in our in our topic here, I just simply put positive and just put simply negative. I put it without the sign. Okay, but in practical, you have positive and negative. So when you have everything here, and you found that the equation now here, is coming from the, look at it, this equation, what you have the equation just now? X equal to E S. What is S? S will be the root of this one. T will remain as T. Okay. Then you have another one, another condition. Look at another condition. And you know that when X, this one with respect to time, yeah, A E S T, you will have this one S A E S T. You have this one S double dot E. So this A will tell you the what? A will be presenting or tell us what? Tell us about the what? Anyone? This A. Hello. Example. We have this one. We have graph. your equation is x equal to EST, isn't it? Then you put, suddenly you have x equal to AEST. Then you have x dot equal to SAEST. So I'm asking you, you have the x double dot becoming x double dot AEST. I'm asking you what is to us now. Anyone? 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 Yes, correct. The amplitude. So where will be the amplitude? This is the amplitudes. This is the amplitude, and this is the amplitude. Will diminish over a period of time. Okay. And if you have, for example, x equal to AEST plus you have BEST, what does it mean now? What does it mean now? What does it mean now? You have two amplitude, isn't it? But perhaps you have another graph, which will give you the same phenomena here. Okay, so that is why here only one x. When we come to here, you will have two A and B. Look at here. Then you have A1 and you have A2. Even though it is pointing just now it's only AB, now it's A1 and A2. The A1 and A2, remember that A1 and A2 is the amplitudes. Is the amplitude of what? Amplitude of vibrations. When you put everything in the equation, becoming as such. So this is very important equation to describe of all these. This is what we call condition. Equation. Do you need to exercise this one, to practice one, to generate equation? At the moment, no. But for the for the option, yes. At the moment, you don't have to this one. Okay. When you come to what they call it, the option, you have to understand this one. But you can also simplify the equation. If you check the equation very carefully, you can also simplify the equation to become very small equation, short equation. This one, this one. It's very light, isn't it? Sorry about that. So I'm going to use a bit thicker. If you look at here, this one can also be represented by omega d, isn't it? So some book, this one, you put it as delta negative zeta plus omega d. In here, I put the whole range of the equation. Okay, now one condition. Remember the three condition? We have zeta less than 1, zeta equal to 1, zeta over 1. And we call it over dam, critical dam, and also, under dam, critical dam, also over dam, respectively. Do we need to understand this one? Yes, this one you have to understand. Also to know about what is the under dam, what is the critical, what is the over dam. Okay, now take the first one. Look at here. The equation that we come from this is coming from the quadratic equation. And as zeta is less than 1, you put this one negative, zeta is less than 1. You put zeta is less than 1. So you're becoming negative. So you cannot solve. You put it J here. J is conjugate, isn't it? And we call this one imaginary. Cannot happen. What is zeta? Zeta, the margin for zeta, remember that the margin for zeta lies between, zeta must be greater than 1, greater than 0, less than 1. And the zeta is exactly as this zeta, yeah? Zeta must be greater than 0, must be less than 1. Likewise, your mu must be greater than 0, must be less than 1, or equal to 1. This one cannot equal to 1. If equal to 1, something will happen. This one, if equal to 1, what does it mean? It will be in stationary statics. Because why? Because why? Because you found that the friction and also the force is equal. Here it cannot be it cannot be equal to 1. So you have zeta less than 1, zeta greater than zeta greater than 1, zeta greater than 1, and zeta equal to 1. But in engineering perspective, this one cannot happen. This one also cannot happen. Why? I will explain later, yeah? So now let's assume that zeta is less than 1. As zeta less than 1, you have the equation, and you will define this one. Why? Because oscillatory. The equation becomes as what we have here. The explanation about it is this one. From the above equation is in the form of oscillatory. Excuse me. Oscillatory motion with the exponential decaying in amplitudes. So it simply means that when zeta is less than 1, your graph will be very much look like as they must be exponential. Oscillatory or motion. You have what just now? Exponential. You have the exponential, correct? What else just now you have? You have the omega d equal to omega n 1 minus zeta square. Okay, the three term, this one, three major keyword to understand about when zeta equal to 1. We call this one underdamping. Look at the next one. When zeta is 1, this one, yeah. So if I can share with you, this one very important. This one I will share with you. Stop sharing. I'm going to share with you the animation part, which is more what do you call it? Interesting, yeah. Look at here. So that is when zeta equal to 1. Sorry, zeta is less than 1 under damp condition. Move to the next one. When zeta equal to 1. Read here. From the above equation, this is the above equation, this is the equation. Up. The motion is exponentially decreasing function of time and referred to a periodic. This one is aperiodic. This one is periodic. This one, yeah, called is periodic. Periodic. This one is aperiodic. Aperiodic, there's no motion, no oscillatory or no oscillation, and the body back to the equilibrium position in the shortest time. How do you basically, show it in the graph? Put it here. Look at here. You come back very short period of time, then you stop. Now decaying. So the graph will be presented by the blue line. Okay, another time. Look at the system. So there is no oscillatory. Next one, when zeta over 1, we call it overdamp. How does it like? Overdamp refer to a periodic also, but no oscillation, but no periodic oscillation with time. So how is it? How do we explain it? Look at here. You found that you take longer period of time to stop. There is no oscillatory compared to the first one. The blue line, this one is for the overdamp. The second one, this one critical, and the last one here is the underdamp. So these three lines very important. We want to explain about the position of the zeta. Okay. You have this one in your notes, but there is no animation, of course, in your notes. And finally, to basically understand how it works, basically talking about damping, look at the three position here. Look at the first one, when zeta equal to 1, zeta equal to 0.1. Can you see the animation class? You have the mass and spring, and this one is material damping. It will be oscillatory quite a while, then it'll stop, isn't it? This one, you put the liquid viscosity, very thin liquid, is critical, so it will go back to the position. So look at the ball here in the water, perhaps in water. Look at another one, liquid with high viscosity, very thick. Typically, it's oil, for example. It takes longer period of time to stop, but still there is no oscillatory. So this one is explain what is basically the damping condition. So the three conditions are very, very important to understand before we start doing the exercise. Okay, any question? Or perhaps it can also be represented by this one. This one, all the material damping, yeah. It is not the dashboard that we learn here. So look at here. You have the overdamp, the red one, you have the green one, the critical damping. Look at the blue one, the underdamp. Again. Okay. Sorry. Okay, I move on. Look at how it dropped. Okay, we'll move on to the next one. Just to share with you damping. This is in our case where you have the dashboards. Look at the critical damping, look at also the overdamp, look at the underdamp. And look at the undamped, there's no damp. The first one is no damp. The second one horizontally, you have the underdamp. The bottom one, you have the critical damping. And last but not least will be the overdamp. So that everyone will be, hopefully this one will know, you have the you have the what, you have the idea what is the difference between damping and the undamped. And the damping is you have the three conditions: critical damping, over damping, and also under damping. So you have the idea to tell or to understand the topic, when you are doing the theoretical or calculation later on. This is the three graph just now I presented just now. This is in color, of course. The green is the critical, the red is the what you call it, the overdamp, and the blue line, this one is the underdamp. This one in book, so many book will be putting in this manner. You can check in book. Just type in effect on damping in Google. You can check this one on your own. Sometimes you stop this one at bottom, sometimes at top. So it depends. Remember about exponential, sometimes you can have a negative side, sometimes you have a positive side. This one all from bottom. What we learn here all from top is as basically the same. Okay? Any question? Any question? Today only theory, so could be bored. If you no one to ask, you can ask now. I will stop 1 or 2 minutes before we go further. Any question?
Doctor.
Yes.
Normally in example of the car we use over them or critical them.
We use under them.
Under them. Oh.
Everything that we use is basically under them. But when we wish something, for example, it can turn up to be over them or critical them. For example, a good question that one. For example, your absorber now of the car is worn off, cannot be used. Or you can see from the absorber itself, you have oil now, a split of oil, isn't it? Like couple of you can see the wet part will be the oil that what they call it is come out from the chamber of the absorber. Okay. You know that when the absorber now is not functioning, when you hit harm, for example, you'll be excited more compared to when you have a new absorber. You will hit a harm with the same speed, of course. Then you find that your head will be reaching the roof when your absorber is not functioning, compared to when you have the absorber with the new one. Your head will be you will be excited, but your head will not reach the roof of your car. So all is about what? Changing the zeta. So the zeta can be equal to 1, can be more than 1, can also be less than 1. But our aims now as the engineer, we have to ensure that the zeta will always be below 1. But in other purposes, you need to zeta to become 1. I will tell you later when we have a time now why we need zeta 1. Some other purposes because we want to inject system more higher. Isn't it? You jump at a trampoline, you jump, then you will be bouncing back with a higher height. So the zeta must be less than 1. Okay. Any other question? I don't know whether I'm answering question or not. But to my understanding, it all is always built on zeta. You can change the zeta as depending on the the system that you want to design, for example. But basically for an engineer, we need zeta become less than 1 to ensure that there will be oscillatory, but it will be oscillatory and will be absorb energy as much as the system can. Okay, if there's no question, I'm going to move to this one. This is now we are going to look on zeta less than 1. We call it the logarithmic decrement. Okay, before that, I will explain this one first, yeah, as usual. So let's now consider, zeta is less than 1. We call it the under damping. Okay, as this under damping, remember the term that we have, the parameter will be the omega n as usual, K by M. We have the omega D, of course, omega n 1 minus zeta square. You also have a zeta here, and zeta, you know that zeta lies between 0 and less than 1. And you also have TD now, which will give you 2 pi by omega. So these are all the parameters. Toward that, you also have C here, so it gives you omega n zeta. Okay, so this is when you have the under them. So let us know you have a system. Okay, you have system. You have system here, a damper. This one K and C is an M, of course. Then you push a bit, X with X dot and X double dot. And as you push a bit, then you let it go or you release, you found that the system will be oscillating. And very much oscillating, quite then it will stop. You have the exponential as what we learned earlier. Then when you look at here, you know that okay, I'm going to measure what will be the amplitude between this one, all the amplitude until reaches 0 here. Amplitude we call one cycle. This one, let's put this as x1, this one be x2. So one cycle, or perhaps we call it one vibration oscillation. One vibration oscillation is equal to 2 amplitude. Equal to 2 amplitude. Remember that. One vibration oscillation or one vibration cycle equal to 2 amplitude. Look at the one cycle, 2 amplitude, x1 and x2. So when we are talking about decremental here, decremental, we are talking about reduction. So reduction of what? Of course, reduction of amplitudes. Amplitude of what? Amplitude of vibration, isn't it? We are talking about vibration reduction of amplitudes. Yeah? So the reduction meaning that from x1, of course, greater, x1 will be greater compared to x2, isn't it? You have x3 here, for example, you're talking x3. So you know that the x2 will be what? X2 will be, perhaps I put it there, x2 will be less than x1, but x2 will be greater than x3. Yes or no? So in mathematics, we can also put this one in the form of what? X2 now is greater than x3, but less than x1. Am I correct? No, sorry. X1. So this is in term of mathematics to tell about this one. To explain this one, you have to look for what you call it logarithmic decremental. Because why logarithm? Because you know in calculator you have log. This one you have the anti-log. Am I correct? Yes, no? Beside anti-log, you also have what? Exponential, isn't it? Log is also exponential. Yes or no? Yes or no? If log x here, you will have x exponential. Am I correct or not? And we don't call this one log because we have log only. You have log base 2, both base 10. You call it ln equal to x exponential. Sorry, wrong. It's not ln, yeah. It's ln x. That is correct. Ln x. This one. This one also log x. Understand me or not, class? So our aims now is to define what? To define the reduction of amplitude between the peaks by using logarithmics. Okay? Look at there, this one. And the term is delta. Is that clear? Anyone? Did anyone respond? I just want to check that way you are still with me. Thank you, Ko. Yeah. So this one, look at here. Okay, now we coming to here. The equation we already done here. This one, remember this one? Isn't it from x1 and x2? X1 or and x2. You can put also x2, s1, doesn't matter. So for one complex exercise here, x1 and x2, and this is the equation. The equation will be different only in terms of TD. One will be TD, one will be with TD, sorry, one will be with TD, one is without TD. TD here. Is it? The second part is TD because you fall here. This one no TD. We'll stop here. So now the next one will be, as you simplify the whole thing because it will cofactor, you'll be getting this one. And finally, you will have x1 by x2 is equal to exponent zeta omega n t. This is very, very important. Okay, I take this one and put it here in my x1 by x2, put it here. X1 by x2 is equal just now what? Anyone can remember the one? x1, x2 equal to 1? Anyone? I just want to check with you, yeah, whether you still with me. So anyone can read?
Exponent omega n TD.
Omega and zeta
TD.
d. Isn't it? I want you to pronounce this one, yeah? Exponent zeta omega. Now, so now, as you, this is, remember this one is the reduction of amplitude. This one also the reduction of amplitudes. Reduction of vibration amplitude, to be precise. You want to get rid of the ln. How do you want to get rid of the exponents? Remember that one? You put it the ln x1 by x2 is equal to, now it become ln. So you have what? You will have omega n zeta t d. What is TD? TD, remember, is equal to what? TD? What is TD just now? What is TD just now? 2 pi by omega t. Isn't it? So you put it here. 2 pi zeta TD is 2 pi zeta TD is omega n. Not to forget, this one will be omega d. Expand the equation 2 pi zeta omega n. This one is omega n 1 minus zeta square. Then you found that this one can cancel. Then your ln x1 by x2 is equal to 2 pi zeta, and this one is 1 minus zeta square. But remember, this one is only for, this one only for x1 and x2, isn't it? Which for one cycle. But remember, your system could have so many mini cycles before it stop. This one, so many cycles before it stop. This one is 2 cycles. We have 3 amplitudes. So you have to modify the equation to become ln x1 by xn. Put it in the bracket. Xn equal to this one 2 pi and zeta. This one is 1 minus zeta square. This is your new equation now, where you have zeta. So this one is for what? Now for x1 to xn, where your n equal to 1, 2, 3, 4, so on and on. And n equal to number of oscillation. Remember that. Okay. Okay, now, if you read book, yeah, if you read books, you found this equation will be in terms of ln, x1 is correct, but xn is correct, but equal to 2 pi, this one r minus 1, zeta, this one most book written as this one. Typically a book written by the Indian scholar, they use this one as the equation. But this equation same as before. The only difference now here, you found that the graph, they presented the graph here. They presented the graph as, look at here, this one is x1, this one is x2, this one is x3, this one is one cycle, 2 cycle, another one cycle, See? So your area is basically number of amplitudes. Remember that it is not number of oscillation. So if n equal to 2 now, 2 cycle, and 2 is 2 cycle of vibration, your equation now become ln x1 by x3, or put it there, just xn equal to 2 pi, your n will be 2 zeta 1 minus zeta square. Am I correct? But in other form of equation coming from other book, for example, I don't want you to mislead the equation, yeah. So here you also have same thing ln, but now x1 correct by xn, put in the n now 3, for example, put in the n 3, for example. So equal to 2 pi r minus 1 zeta. This one is 1 minus zeta square. So r minus r minus 1 is equal to how many amplitude you have? If you use this equation, how many amplitude? 1 amplitude, 2 amplitude, 3 amplitude. So you have 3 minus 1 is also 2. So you have 2 here, you have 2 here. So the equation is very, very similar. It's not similar, it's the same. Do you understand me or not? So you can use you can use equation from any other book, but you have to check what are the parameters represented from the graph. In the books that I that I would in my books, perhaps the n will be representing the one cycle vibration or one complete vibration oscillation. Same thing, yeah. In other book, you put r here is basically number of amplitudes. Okay, class. Any question? No, so we move to the next one. This one just to share with you, sometimes it is not in the form of what you have this one. It can also be in the form of here. I think in a couple of semesters back, I used this one in our equation. But very unfortunate that students do not know this one coming from the equation. This one we manipulate the equation, we arrange the equation, we be getting the other form of equation. This question: do we need to we need to memorize? No, you don't have to memorize this one. What you need to memorize is this one. This one you must memorize. You cannot, because if you don't memorize, you have to generate your own equation. It's very much difficult because you start with the equation that you have so many unknown parameters coming from the exponential equation earlier. Okay, this one explain everything. You have this one, your books, in your books. As I mentioned earlier, what is the equation just now. The other thing that I would like to emphasize here, yeah, look at the equation that ln x1 by xn, for example, yeah, equal to 2 pi n zeta 1 minus zeta square. If the equation tell you that the initial, or after, let's put it here, after after four after four vibration oscillation, the amplitudes, the amplitudes, the amplitudes become 1/100 of the initial. This is very common in the equation. So now, do you understand about this term? After four complete vibration oscillation, this one 4 complete. Can anyone answer me? N equal to 1? N equal to 1? N equal to 1? So if you don't put interest in this one to answer this one, so I will just skip this one and you have to do on your own. 3. Read the question very carefully. After 4 complete vibration oscillation. So N equal to 1? 4, correct. Your Xn equal to 1? Your Xn equal to 1? Okay, no one interested to answer. So is Xn equal to 100? It's not correct. It's not correct, Fong. It's not correct, Tan. Look at here. 5 is not correct. The amplitude, look at the oscillation. The amplitude is what? Is 1/100 of the initial. So your Xn equal to? Yes, it's not correct. 0.4 is not correct. Your Xn equal to? Anyone? Last one. 4 is not correct, or is 1/10. Sorry, 1/100. So now my big question is, what is X1? Anyone? You don't want to answer this one? I just leave it like that and you think about it on your own. X1. 1 is not. How do you know 1 is correct? How do you want 1? How do you know 1? Because there's no unit, yeah. Because there's no cm, there's no meter, there's no millimeter now. How do you know it's 1? Is correct, but how do you know? My question, how do you know? Initial is correct. You can use initial when we study 2 degree of freedom electron. You can put initial as 2. But now, why is this 1? It's exactly 1. Why? And then one more answer. And then I explain this one. You can't simply take this one as 1. You have a reason why you take this one. Because given numerator, Tan, because, look at here very careful, because by doing what you call as, by doing normalizing. By doing normalizing, meaning that let x1 equal to 1. This one is by doing normalizing. Okay, look at the y, because we're doing normalizing. By letting x1 equal to 1. Always. Regardless any circumstances, this one is always x1 equal to 1. Okay, I think we come to end another 70 minutes. Let me check my notes. Is it come to end? This one, I think when I meet you again, inshallah, tomorrow at 10, I'm going to show with you example number 3. Before we stop, I would like to, any question before I make my highlighted notes? Any question? Any question? Or you don't want this? You don't need, we can just we can just close the session so I can meet again inshallah tomorrow at 10. So do you interested to know the highlighted notes? Yes or no? Okay, thank you. The highlighted note is one will be the system that we are dealing with is this one. K and C. you give a push or you pull it down with x dot x double dot. It will create you that the mx double dot plus cx dot plus kx equal to 0. You can also simplify the equation to become as such, plus k by m equal to 0. And this one, you can also create this equation to become another form equation 2 omega n zeta x dot plus omega n square x equal to 0. So this one is what we call a differential equation of this system. So that is one. The other one we introduce the C equal to 2m omega n zeta. We also introduce that your omega n equal to k by m square roots. And that also will give you TD, there is no Tn now, equal to 2 pi by omega d. Okay, the three conditions that we're dealing with, one is zeta equal to 1, zeta less than 1, zeta greater than 1. This one is critical. This one is what we call the underdamped. This is our concern now. Under damping. This one is over damping. It is beyond of our topics to discuss more about it. Yeah? Okay, so when critical, your C now equal to 2m omega n zeta. And you know well that critical meaning that zeta equal to 1. So therefore, your CC equal to 2m omega n. Remember that one, yeah? You have CC now. CC is critical damping. So in other words, you can also put this one as you have C by CC is equal to 2m omega n zeta is equal to m omega n. You can automatically cancel it off. This one will give you zeta. And in conclusion, you know that zeta is very much high compared to 4 times or 5 times of the actual C. Okay, so that is one. The other part is in during oscillatory, or perhaps in other words is what we call is underdamping. You will have reduction of amplitudes. You have the reduction of, we call it as decremental of amplitudes. And because the graph that is shown for the for zeta is less than 1 in terms of exponential. This one, yeah, exponential, and also exponential. This one is x equal to EST. So you have the amplitude of reduction of amplitudes. So you will have what? You will have ln x1 by xn equal to 2 pi, put it at n, zeta 1 minus zeta square, where your n is equal to number oscillatory or vibration, and your zeta, as usual, as I mentioned earlier, which is zeta lies between, zeta must be greater than 0, must be less than 1, and your xn will be the final amplitudes, which is very small, isn't it? Which is very small, which is very small, and less than 1, and last but not least, your x1 is always 1 due to normalizing activity. So if you can understand this one, inshallah, a week ahead or next week or tomorrow, yeah, we are going to do the exercise or the example. You can totally understand. So we are reaching our times, 9:15. So any question? I really hope that you can catch up, or you can absorb the thing that we discuss here, to ensure that in the coming lecture, we can do all the exercise and you basically understand the principle of a thing that we calculated. Because when you come to solving the equation or problem, there will be no theory basically. We are going to put all numbers, but you have to understand that where the numbers come from. Okay, any question? 1 more minutes. Any question, class? So if there is no question, thank you very much for being with me. Thank you very much for attending and also participating in the class. Typically for those who are very concerned answering all questions, even